Hello and welcome back to Calculus 1. We have exam 3 review. So we already went over the list. It's on chapter 4. There will be a problem that will ask you to look for critical points and then determine min or a max. Then one problem for the first derivative test, and I said with analysis, and that analysis means at the end of the problem you have to state intervals of decrease and increase. You also have the second derivative test separate problem, which is going to be again with the analysis, and that would be concavity. And then we have graphing. Now graphing is going to be the problem where you are given everything and you are supposed to put all of those into one graph.
Are you going to give us like the first derivative, and then we'll have to figure it out from that?
No.
Or are you just going to tell us it's increasing on this?
Yes, I'm going to tell you that the first derivative is positive on the interval so and so, negative on the interval so and so. So you need to know that the negative derivative on the interval means function is decreasing. I'm not going to say function is increasing. I'm going to say derivative is negative.
Okay.
And then you know that's decreasing. Concavity as well, and vertical asymptote, whatever else is there. So that's graphing. Linearization, which is tangent line. So you can either use the formula from linearization that you memorized, or if you haven't memorized that and you know that linearization is the tangent line, you can use the tangent line procedure from chapter 3. Differentials are the word problems usually, where you are looking to approximate the change, and you are approximating change with the dy. So that's another type of a problem. We have optimization word problems where you set up two equations, plug one into another, take derivative, and solve. So usually the issue there is, modeling. L'Hopital's rule has a lot of different possibilities. So we know 0 over 0 and infinity over infinity are the main ones that you are looking at. But then we also have 0 times infinity, infinity minus infinity, 1 to infinity, 0 to 0, and so on. So you have those other types. Antiderivatives are the basic integrals, right? So you are looking at the basic integrals. You need to know how to integrate. There will be no limits, so no calculation of limits as definite integrals, just indefinite integrals. And remember that it's either plus c or minus 1 per problem, right?
That is plus c or minus 3.
Okay, I'll bump it up to minus 3 then. So if you, by popular demand, if you forget plus c, instead of losing 1 point, now you'll be losing 3 points.
Well, if we just write down plus c, then we get 3 points.
No. And then you have mean value theorem. A mean value theorem was the theorem, guys. You need to learn the statement and the formula as well. Statement says that if the function is continuous and differentiable, then the formula applies. If any of the two conditions are not satisfied, the formula will not apply. So you have to be very careful about the statement of the theorem. So learn the statement and learn the formula. At this point, I would like to ask if you have any questions on problems that you would like to see how to do, something from homework or whatever. Yes.
Can we go over a mean value theorem problem, like just to how to apply it?
So,
I know the
okay.
formula and everything.
So mean value theorem states that if the function is continuous and differentiable on A to B, then the derivative at some value C that is between A and B is f of B minus f of A over B minus A. So I'm going to pick up a problem in, you guys, you should be giving me the problems from these sections. because I don't want to deal with situation O, but it wasn't the same one you did in class as the. So you should be picking the problems, not me.
How about page 295, problem 12?
Problem 12.
Yeah.
Okay. So we have that the g of x is given as x cubed minus x squared minus 5x minus 3 on the interval -1 to 3. So we have to calculate f of 3 minus f of -1 divided by 3 minus -1, and that needs to be equal to the derivative at c. So we are going to find the c for which this goes. Now, is this continuous? Yes, it's a polynomial. Is it differentiable? Yes, it's a polynomial. So it's very easy for polynomials to claim all of those things. So now f of 3 is going to be 3 cubed minus 3 squared minus 5 times 3 minus 3 minus, and now we have -1 cubed minus -1 squared minus 5 times -1 minus 3 divided by 4 equals to the derivative of this. When you plug in c is 3c squared minus 2c minus 5. You see, I plugged in c for every x, because when you take the derivative in respect to x, you're going to get f of x, f prime of x, and then you plug c for every x. So I did that everything in the same line. So now I have 27 minus 9 is 18, right? And then 18 minus 15 is 3. Is it 0? I think I got 0 there. And then I have a -1 minus 1 plus 6 minus 3 over 4 to be 3c squared minus 2c minus 5. One more time. 27 minus 9 is 18, minus 15 is 3, 3 minus 3 is, yep, I'm getting 0 there. So negative now, first of all, in parentheses, we are going to have 1, right? So I'm going to have a -1/4 equals to 3c squared minus 2c minus 5. So we need to solve for c, and I need to move the 1/4 to the other side. We're going to get 3c squared minus 2c minus 5 plus 1/4 equal to 0. And from there we get, now what I'm going to do is I'm going to use the Wolfram Alpha solver, because I'm not going to sit here 30 minutes figuring out the quadratic formula with 19 quarters and stuff. So Wolfram Alpha, and I'm just going to say, now obviously for the exam you shouldn't be having these crazy numbers like this. So solve 3x squared minus 2x minus 5 plus 0.25 equals 0. What we have as the answer is, and the approximate form, we have x to be either -0.968 or x equals 1.635. So if you're looking at these two values, the interval is -1 to 3. Both of these values fall inside that interval, so both of these are okay. These are c's, sorry. So we have two c values where the average rate of change is equal to the instantaneous rate of change. So on the left-hand side, you will be computing the average rate of change when you plug the numbers that you got in the interval in the formula, which is the function. And on the right-hand side, you will find the derivative of it and then plug C. And then at the end, you will solve the equation, whether it's exponential, trigonometric, in this case was quadratic. So you will get some type of equation that you should know how to solve from your previous life, which was either pre-calc 1 or algebra. Sounds good?
Yes.
All right. Do you have any other questions regarding material from chapter 4?
Can you show us how to do the estimating and approximate value of linear approximation for like cosine 31?
Cosine of 31 degrees. Excellent. So in order for us to find the cosine of, now you want a linear approximation, linearization, right? Not differentials.
Yeah, no.
Okay. So linearization. We are going to pick a value A to be 30 degrees because that is close to 31 degrees and it's good and easy for calculation. Linearization formula L of x is f of a plus f prime of a times x minus a. This 31 will be x later on. Right now we are going to just use 30 as means of calculation. Now we also see from here that the function f of x is cosine x, whose derivative, which we are going to need, is negative sine x. So now we get to plug everything in the formula. L of x is equal to f of a, so that's going to be cosine of 30 degrees, minus sine of 30 degrees times x minus 30. Remember that a is 30. So you are going to have that L of x is equal to cosine of 30 degrees is going to be root 3 over 2 minus sine of 30 degrees is 1/2, and you have x minus 30. Now you want to so this is a formula now. It's actually a tangent line.
That's the tangent line form.
So you either memorized the formula or you did the tangent line procedure to get to the same spot. And now you want to know how much is cosine of 31. So cosine of 31 degrees is approximated by L, computed at 31. So we have root 3 over 2 minus 1/2 of 31 minus 30. So the whole thing is root 3 over 2 minus 1/2, which is approximately 1.72 over 2 minus 1 over 2, about 0.72 over 2, which is about 0.36. So you can try to use the calculator. Just make sure that your calculator is switched to degrees, and take the cosine or sine. Take the cosine of 31. So first go to mode and change to degrees, because your calculator should always be in radians. Your calculator should be in radians because I hope the only thing you use the calculator for in trig is to graph trig functions. And the only way you can graph trig functions is if the calculator is in radians. So that's why now we have to switch it to degrees. And then hit with the cosine of 31. And this is really off. I don't like it. I'll have to recheck my calculations. The calculator claims that the cosine of 31 degrees is approximately 0.857. And we have 0.36. Now, being that we are on the range -1 to 1, that's a huge margin of error. Let's see. So we have cosine of 31 degrees. We are going to use 30 degrees there. Derivative of cosine is negative sine. The cosine of 30 is root 3 over 2. Sine of 30 is 1/2. Ah, this over here cannot be, A is 30, but this need radians. I cannot plug in 30 there. I just noticed that. That's the mistake. So this 30 cannot be 30. This 30 has to be in radians, and that is pi over 6. So this is 30, which is pi over 6. Which means that this is pi over 6. And the 31 that I need to plug in also needs to be converted to radians. Now the conversion factor to radians, right, is pi over 180 degrees. So this is going to be 31 degrees, right? And then degrees and degrees will cancel. So what I have to plug in over here is 31 pi over 180. That's much better. So now result has to be much better than what we had. So this works out to be, I need the common denominator, right? I need a common denominator here, which is times 30. So it becomes pi over 180. Becomes pi over 180. So root 3 over 2 minus pi over 360. Now let's see what that gives us. So this calculation, when you plug in the calculator, gives us 0.8573. And look at that. You have to plug in radians. You cannot plug in degrees in a formula. Well, we have to put it somewhere, but can't be a lot. You can have integration question with trig. You can have graph trig. You can have first, second derivative for trig. You can have linearization and mean value theorem. So most of the concepts could have a kind of easygoing trig function through it. But then your Calc 2 is just trig all the time. So, you know it. Any other questions you might have in preparation for exam tomorrow? Any other questions? Going second time, asking. Yes?
I'm not in trouble with 3 to 34 for the linear approximation. I'm having a lot of trouble with them. I don't know why.
Yeah, you got me on that, right?
Problem 34.
Well, no, it's not. It's just on. It's on the MATLAB.
So what does it say?
It says use linear approximation to estimate the following quantity. It's 3 to the 34.
Like this?
Yeah. Oh no, like 3. That's true. The cube root of 34. Yeah.
Cube root of 34. This. And they want a linear approximation for this. What is the closest cube root to 34 that we know how to take? 27.
That's what I was thinking.
So we have that f of x is equal to cube root of x, and a is equal to 27 because that's the convenient number that we can compute.
Then x equals 34.
And then, yes, later x will be 34. Very good. So now what I have is the linearization formula. We already know it. F of a plus f prime of a, x minus a. So that's function computed, so cube root of 27 plus, and now I need the derivative, right?
So that'll be 1 over 3 to the cube root of 27 squared.
27 squared, nice.
And then
X minus 27, nice. So now, cube root of 27 is just 3 plus, and this term is 1 over 27 altogether. Yep. Because the cube root of 27 is 3, 3 squared is 9, 9 times 3 in front is 27, and we have x minus 27 here. So this is your linearization equation.
oh wait, is that x minus 27?
Yes.
Oh, I thought x equals 34, so don't you do 34?
Well, that's next step.
Oh, okay.
So cube root of 34
So that right there
is approximately equal to linearization computed at 34, which is 3 plus 1 over 27, 34 minus 27, which is 7.
Yeah,
3 plus 7 over 27.
Yep. So 3 plus 7 divided by 27, I get 3.26 or 259.
There you go. So now we can check and see how the cube root works. So, oops.
So now to check it, technically.
So cube root of
34, right?
34.
Which is 3.239.
Cube root of 34 is approximately 3.240. It's pretty damn close.
Yeah. All right.
Yep. So we're good.
Thank you.
We are 2 cents away. Anything else that you might be interested to review?
I think critical point.
We actually, well, we have 2 things. Or where derivative does not exist. So those are the 2. What happened? Yes, there will be L'Hopital rule, which means, well, there has to be at least maybe part A and B for L'Hopital rule. Which, do you have a question in mind? Well, find the problem. We can take a look. It's about page 300.
And we have 37.
What's the page?
307.
Okay, 307. Problem number?
37.
All right, guys. Problem is on L'Hopital's rule now.
Ooh, do like infinity minus infinity.
I can.
What problem?
No, 1 minus 1.
So this is problem 37, and it has 3x to the 4th minus x squared divided by 6x to the 4th plus 12.
And what was the question?
Solve the limit. So now you're looking at this problem and you already know what the answer is because you did Calc1 limits. Answer is 1/2. But now we want to use L'Hopital rule to show that that answer is 1/2. So what we do is we plug in infinity and we have infinity over infinity.
So limit.
So that means that we can take independent derivatives of numerator and denominator. We get 12x cubed minus 2x divided by 24x cubed, and that's it. So now we plug infinity, and you see it's still infinity over infinity. You do it again. L'Hopital's rule. So now when I do the derivative, I get 36x squared minus 2 over 24 times 3 is 72x squared. Exactly. Do it again. Another L'Hopital rule with the limit x goes to infinity, because we again had the infinity over infinity. So now we're getting 72x over 144x. And you see now that they cancel down to 1/2. Yes. Which problem? All right. The next problem is 45. Ooh, nice. Limit of x cosecant x, and this over here, x goes to 0.
For this, you gotta do the reciprocal, the x.
Yes. Or cosecant.
Oh, you can do either one?
Either or. So now we are getting a problem. Now these problems are very frequent on exams, and you have x cosecant x when it's 0 times infinity. Now when you see 0 times infinity, the trick is to take one of the two functions and write it as 1 over f, because in that case the function that you had issue with is going to become the function that is easy to deal with, because they will both have the same, well, actually, let's see. So we are first going to transform this integral into limit into limit x goes to 0,
I think we should transform it close.
x over 1 over cosecant x. But you know what the 1 over cosecant x is, right?
Yeah.
What is it?
Sine.
Sine.
So then sine of 0 is 0.
So now you have 0 over 0.
Still gotta do it.
So we do L'Hopital rule. Well, we haven't done L'Hopital rule so far. That was algebraic manipulation. Now we are doing L'Hopital's rule. L'Hopital's rule takes derivatives. So we have 1 over cosine x, which is?
Cosine of 0 is 1. So you get 1 over 1.
Yes. Anything else?
Got you, Ben.
1 over x.
What happened?
1 over x.
1 over x.
Well, you have right up there in the middle of the blue.
1 over f.
Over f.
Yeah.
I gotta get this on Snapchat. That's Snapchat worthy right there.
Do it for snap.
Dude, you could have did it, I wouldn't have cared.
Yeah, we're gonna do that too.
Anything else?
Anything else?
I'm still not ready.
I've got to.
Optimization. Those are really easy though.
Any other questions? Yes.
Can we do some optimization problems with
Which one?
like the garden plot where you have two different like you have the outside square and you have the inside square.
Ah, I know exactly which problem you're talking about.
Yeah. Yeah.
Now I gotta take it off the test. No, I'm just kidding.
Oh my god. That was on my mind.
So the trick with optimization There it is. So it's optimal garden. That's the name of the problem. It is 4429. And what you have is the rectangular flower garden, and then there is a grass border. So say you have, this is the garden, and you have a border. The border is 2 meters on each side and 1 meter on these sides. The flower garden needs to be 30 meters squared. And they're trying to figure out what is the what are the dimensions of the garden would minimize combined area of the garden and borders. So what I'm going to do is I'm going to label X and the Y on sides, and then they're looking for area, combined area, that's everything, right? So now I have to figure out what are the dimensions for the sides. So what would be this dimension here, looking at the sides up there?
Would it be x plus 4?
X plus 4. Because you have X dimension, and then you have 2 meters on each side, so 2 plus 2 is 4. And how about the top? Y plus 2. So now overall area that they are looking to minimize is X plus 4 times Y plus 2, and that needs to be minimum.
Oh, and then you just solve for other x or y.
You have the other equation, xy is 30, right? So I have equation x plus 4, y plus 2 needs to be a minimum, and from here I have that y is 30 over x. Plug in, and we get x plus 4, and then y is 30 over x plus 2 equals a minimum. Multiply out all of it, so that's x's cancel, we get 30 plus 2x plus 120 over x plus 8 equals a minimum. The whole problem now is 2x plus 120 over x plus 38 equals a minimum, and now you can hit it with a derivative because you have only one variable. It's simplified, and you have only one variable in there. So that's 2 minus 120 over x squared equals to 0. Because 120, you copy 120, the derivative of x to the minus 1 is minus x to the minus 2. Yep, that's all good. So now 2 is equal to, you're just solving this equation. 2x squared is equal to 120. X squared equals to 60. X equals plus minus square root of 60, but the lengths cannot be negative, so it's just plus root 60. And the largest value you can pull out is 4, because 4 times 15, so we get 2 root 15 meters. For x, remember that y is equal to 30 divided by 2 root 15. That's 15 root 15, and we hit it with root 15. So it just gets to be root 15. So the dimensions are 2 root 15 by root 15 meters. And those dimensions of the garden will minimize the combined area of the garden, preserving the middle of the garden to have 30 meters squared to plant the flowers. Now this problem can be it's the same calculation, but what you are getting is the, let's say, the margins on a textbook. You know how the textbook, if you take here, I'm going to take this textbook here. If you observe, each textbook has margin on the bottom, margin on the side, margin on top. This problem with the garden is exactly the same as the problem that if I would ask, what are the margins of the page so that you can minimize the area of the page? Why would I want to minimize area of the page while keeping certain area in the middle? Clearly, I want the area in the middle because that's where the content goes, right? But why is my goal to minimize the size of the page? Yes. So you make the book smaller, which means smaller paper means less cost, right? So by minimizing the page. So you say I want so and so many inches squared of area where I'm going to put the text and theorems and pictures and everything else. And then the margin needs to be 1 inch off the side or 2 inches and so on. What's the minimum page? Right? You can actually do that. It makes sense. Any other questions?
Wait, quick question about that. So say you ask for the horizontal, if the numerator is greater than 1, then the denominator, it's a slant. So that would do the
long division.
Then when do I divide by the greatest denominator exponent? When do you do that again?
When you do the limit, we did with the L'Hopital 15 times. All right, anything else, guys? Anything else for the second time?
Can I do a graph?
Graph, which one?
Yeah. What else we do? I don't care. How about
Brian, I'm sure you have that
graph? How about x ln of x? Graph. Or wait, you choose one that's closest to the test.
X, ln x is good.
Okay. Okay, so
All right, graph problem, guys. To graph a function, we have to find the intercepts and all that kind of stuff. So x-intercept is when y is equal to 0. So we have x equals to 0 and ln x equals to, oh, first of all, domain over here. So domain is 0 to infinity because ln x has the restrictive domain 0 to infinity. So now we have x equals 0, which we have to throw away because ln x doesn't work there. And we have ln x equal to 0. If you e both sides, you get x equals to e to the 0, which is 1. So we have 1, 0 as the x-intercept. The y-intercept is when you set x equal to 0, but we know we can't, not in the domain. So far, we have one piece of information. The next part are asymptotes. So we did domain, we did the intercepts, now asymptotes. There is the vertical asymptote at 0, x equals 0, because of ln. No horizontal asymptotes, no slant asymptotes, because neither of these functions have them. The next one is the first derivative test, so we need to take the first derivative. X ln x, that's a product rule. So copy the first derivative of the second plus copy the second derivative of the first. We get 1 plus ln x. And you know that I like to take second derivative right away, which is going to be just 1 over x. So now that I have both of the derivatives, first derivative test should be quick and easy when we take the derivative and set it equal to 0. ln x needs to be equal to negative 1. When you e both sides, you get that x is equal to 1 over e. E to the minus 1 is 1 over e. And the y value for that is 1 over e ln 1 over e. So that's over here negative 1. So minus 1 over e. So we have a critical point at 1 over e, negative 1 over e. So that's the critical point. We are going to do the partition starting at 0, partition at 1 over e, going to infinity. Remember, the vertical asymptote is at 0 and domain does not exist left of 0, so we don't need any of that stuff. We need to pick 2 test points, and at test points now, since you are plugging into equation that has ln x in it, I would like to pick numbers that are e based because that's easy to compute. So I'm going to pick e, and I'm going to pick 1 over e squared, because if I make the denominator bigger, the fraction gets smaller. So 1 over e is the critical point. I'm going to pick 1 over e squared, because, as I said, it's easy to compute. So now the first derivative computed at 1 over e squared is actually 1 plus ln, and I'll put e to the minus 2, which is 1 minus 2, which is negative 1, which is negative. So we know that we have a decrease right here. Compute the first derivative of e, which is 1 plus ln of e, which is 1 plus 1, which is 2, which is bigger than 0. We have an increase on that part, which makes the critical point a minimum, because we have eyes and we look at it and we see that the function decreases and then increases, which gives us a minimum. And then you can write the answer for this if you're interested. So f of x is decreasing on 0 to 1 over e. F of x is increasing on 1 over e to infinity. Now that is piece information that we need. This is also a piece of information that we need. The next part is the second derivative test. We are taking our 1 over x and we set that equal to 0. And that has no solution. And because it has no solution, that means that no inflection points. No inflection points. So now, partition is just one big partition, 0 to infinity, and you can pick anything you want. Now, can you pick e? Sure, you can pick e, but why? There are no ln's in the equation. You want to pick something that it's easy to compute, so we pick 1. Second derivative at 1 is 1 over 1 equals 1, more than 0, so everything is concave up. So f of x is concave up on 0 to infinity, which is actually entire domain. So now to graph, We don't need to draw anything to the left because there's no domain there. We have a vertical asymptote at x equals 0, which is the y-axis. We have the x-intercept at 1, 0. And we also have a point 1 over e, negative 1 over e. So now we need to approximate how much 1 divided by e is. You can do that on the calculator. So it's about a third. It's 0.368. So it's about 1/3. So we have a point here, which is a minimum. So the function, in this case, will start with the open circle. Remember, you can't go and follow the asymptote because you would have to cut through the x-axis again. You're only allowed to cut once. So the function will just do this. It's always concave up. You'd see it's decreasing before it hits the minimum value. It's increasing afterwards. It's concave up all the time. And the most important part is that there is this open circle because you cannot have a value there because ln cannot be computed at 0. It's negative infinity. That's the open circle, and then at the origin, and then the function emerges, goes, makes a minimum there, goes back up, and everything is concave up. So the entire domain is concave up, and we have decrease and increase. That was your graphing problem, x, ln x. Any other questions, concerns? Yes. Yes, on Thursday you have labs and project, and it's a final exam day. Yes. Final exam is 5 to 6, but I will be here earlier to answer questions. Probably have office hours as well. So I will be here. I'll probably be at school at 4, maybe even earlier. Our final exam starts at 5, so if I'm not in the classroom, I'm in my office. If you have any last-second questions. And those questions cannot be, can I bring the project tomorrow, which is Friday, because the school is closed. So you can't. Whatever you can in on that night. And homework will stay open until midnight Thursday, whatever is open. So anything that you do till midnight online, anything that you hand in of labs, class preps, homework by hand, including the project, obviously, will be taken into consideration for grading. All right, any other questions for the exam to end the stream if there are no more questions for the exam? Exam review questions? No? Easy? All right. Well, I just did